Hello friends, students, and people who clicked on this video because there's a guy in the tree with no shoes on in the thumbnail. It is a beautiful day out today, and what better way to spend it than by learning some calculus. Today's lesson is on the washer method for finding volumes. But first, I'm going to need to go off into the woods and pick up some sticks. Bear with me. Oh, I didn't see it there. What were we talking about? Right, the washer method. But let's build up to it. And centrally, we need to understand that this is all about cylinders. And how do we calculate the volume of a cylinder? Various kinds of cylinders. We can start with our basic cylinder that you're familiar with. It's just, a cylinder. Simple stuff. And you know the formula, of course. Pi times the radius squared times the height. Easy peasy. That's pretty simple. But what if it's a weird cylinder? What if it's kind of a funky cylinder? Well, then it gets a little more complicated. And when I say cylinder, I'm going with kind of a broader definition of cylinder here. Like, I'm talking about those weird vases, the fancy vases. You see them sometimes, they kind of go like, ooh. Or like a pawn from chess. And these things are cylinders, well, they are cylindrical, more accurately, in the sense that if you take a cross-section of the cylinder at any point along its height, like that, well then, you're going to get a circle. The cross-section is going to be circular. So for a shape like that, how do we find the volume? Well, there's a way to do it. So let's imagine that weird vase again. It's very buggy out here, sorry about that. Vase. Imagine a vase, which is weird. It goes like in and out. So you can't use the regular formula. And I'm holding this vase, imagine this vase, in my hands. And now imagine I turn it sideways. That's going to be just helpful for us. Make it a little easier. Okay, I'm holding this vase in my hands, and we have like a coordinate plane. A Cartesian grid. Classic coordinate plane. I'm gonna hold this vase so that the end of it, the base of it, is now flush with the y-axis. Keep that in your head. And that means, because it's flush with the y-axis and it's centered in the middle of the grid vertically, that means that we can sort of draw an invisible line going through the whole thing. The middle of the center, down the center of the vase, which will line up with the x-axis. I want you to imagine this stick is the x-axis. Here's the base of the vase. Here's the x-axis. Make sense? Alright, and what this means now is that we can take the radius of each of those cross sections that could be a circle, they're like this now. Those radii can be a function on our Cartesian grid, like this. Now, let's take this other stick. Imagine at the end of this stick is a point on our function, a point on the edge of the vase. Now let me turn this so you can see it. What happens if we rotate it all about the x-axis? Well, then we're going to do something like this. And what have we done? We've traced out a cross-section of the vase. And if we do that along every point of the vase's height, which is now length because it's on the x-axis, but it's still height, it's the height of our vase, and we add all of those cross sections together, we integrate, now we're getting to the calculus of it all, then, boom, volume. Alright, so our general formula for finding the volume of our cylindrical object is this formula. Let's go through it piece by piece, starting with our integral sign, because we're integrating. A and B are our limits of integration, meaning it's a definite integral. A is where the base of our object is, B is where the top of it is, B minus A is the height. Now, pi f of x squared, that is the formula for the area of a circle, only we've subbed in f of x for r, because r is no longer a constant. R is changing from A to B along the height. So, we are integrating every single one of the infinite number of circular cross-sections that we could cut out of our object along its height, and we're integrating them all to get our volume. Dx right here ties the whole integral together. And now since pi is a constant, if you want, you could also move it out here, outside of the integral if you like. Doesn't really make a difference, kind of up to you. But just remember that pi is a constant. F of x, not a constant. F of x is variable. Okay, so this has absolutely no relevance to anything at all, but I really want you to look at these ducks. Okay, so that was quite a bit of setup, but now it's washer time. Now, for those of you who have never assembled any furniture, a washer is one of these little metal doohickeys, like this. And it's used for fastening screws. So, what's the washer method? Well, you might have noticed that that little washer thingy, it's kind of like a donut. It's got some thickness to it. And the washer method is exactly dealing with that thickness. It's how do we find the volume of a cylindrical object with a cylindrical hole going through it, not just a solid object or, a fully hollow container. How do we do that? It's pretty simple, actually. We're just going to use that previously discussed method twice. First, we're going to calculate the volume of the object if it didn't have the hole in it. In other words, we're going to use the outer radius. Then, we're going to calculate the volume of the hole. In other words, we're going to use the inner radius, and we'll subtract the latter from the former. In other words, if you imagine the outer radius as f of x, the inner radius is g of x, it would be, the integral from a to b pi g of x squared, pi f of x squared, that's my bad, dx, minus the integral from a to b of pi g of x squared dx. We can simplify this a little bit by first of all we taking the pi out of the integrals, then factoring it out altogether, and then we can also use our sum and difference integral rule. Sorry, birds, I don't know if you can hear that. Sum and difference integral rule. So we now have pi times the integral from a to b of f of x squared minus g of x squared. And this is important because you can make a mistake here, is we're taking the difference. Geez, that bird is really loud. I'm gonna sound crazy if you can't hear that, but I swear that there's a bird. And it keeps interrupting me. So inside that integral is f of x squared minus g of x squared. And this is very important. We are using, okay, this bird, I'm gonna kill that bird. I'm gonna you're gonna see me eating that bird in the next shot, just chomping on its head. I'm joking, by the way. Don't call the EPA. Are you done? Okay, I think he's done. As I was saying, it's very important that you take the difference of the squares and not the square of the difference. And it's an easy mistake to make because we do take the square of the difference when we're dealing with finding the volume of objects that have square cross sections, or triangular cross sections, or rectangular cross sections. Then we do take the square of the difference, f of x minus g of x in parentheses squared, as opposed to f of x squared minus g of x squared, which is what we're doing here with the Washer method. I, of course, have never made such a mistake, but people do. And now you won't either, because you've watched this video. And that's basically the Washer method. It's pretty simple, right? Alright. Before I let you go for today, I'm going to give you a little practice problem. And now this problem, it's a little tricky. It's going to require a little lateral thinking with how you apply the Washer method. But I think you're going to get it. Now would be the time to go grab pencil and paper. If you don't already have those, I'll give you a sec to pause the video and do that. Alright, you got them? Here's the problem. You're a jeweler, and you need to make a bracelet. This bracelet is a torus, or a donut shape, and it is 9 centimeters in diameter. So that's from one edge to another, outer edge, and it is 1.5 centimeters thick. That's actually really all the information you need to solve this with the Washer method. But if you need a hint, then I'm gonna stop talking for a second, so that those of you who don't want a hint can pause the video and try and do the problem. But for those of you who do need a hint, just I'll give you one. Alright, so if you need a hint, I'll tell you that in order to solve this problem, you're also going to need the circle formula, the formula for graphing a circle. And if you forgot, that formula is x minus k, k being the center, the x-coordinate of the center point of the circle, and that's squared, x minus k squared, plus y minus h squared, h being the y-coordinate of the center, and all of that equals the radius squared. Alright, now I'm going to pause again, so let you pause the video and solve it. Alright, do you have your answer? The correct answer is 41.637 cubic centimeters. That is the volume of your bracelet. Now, if you got that answer correct, you can skip the next section of this video. But if you didn't, I am going to go through it step by step and show you how to do it. Alright, so here I've got all of the work laid out. Let's go through it step by step. First of all, our basic information. We're finding the volume of a bracelet, which is a torus, and it's 9 centimeters across and 1.5 centimeters thick. Our formulas we're going to need: the Washer formula, right here, or you already know that, and the circle formula, which I also just explained. Now I've got this graph here, which sort of shows what we're going to do. Basically, this is a cross-section of the bracelet, which we're then going to rotate around the x-axis to form the entire bracelet, sort of like this. And the center of that bracelet, of that cross-section, that is the point 0, 3.75. So that's our K and our H. We'll start with that. Let's rearrange our formula. So we've got everything plugged in right here, and then we just sort of rearrange it. We resolve that, we move x squared to this side, right? We take the square root of both sides, note that it's plus or minus, and then we add 3.75 to both sides. So we end up with y equals plus or minus the square root of 0.5625 minus x squared plus 3.75. So therefore, f of x, the top half of our circle, is that where the root is positive, and g of x, the bottom half of the circle, is that where the root is negative. Now let's plug that all into our washer formula. V equals pi times the integral from negative 0.75 to 0.75. You can see those up here are the limits of integration, because that's the whole area we're working with, of f of x squared minus g of x squared dx. And you can plug that into your calculator yourself. Use Math 9 for the integral, and you will see it is 41.637 cubic centimeters. Oh, you're still here? That's all I got for you. I hope this video helped you understand finding volumes with the washer method, and I hope you have a great rest of your day. As for me, I gotta head out before I get eaten alive by insects. See ya.